Welcome back, everyone. Look, if you're a focused learner wanting to really peel back the curtain on the mechanics behind cutting-edge student robotics, you are absolutely in the right place. In today's Explainer, we're doing a deep dive into the technical documentation of the Oceaners team from their 2026 MATE ROV campaign. And we aren't just going to look at what they built, we're going to explore exactly how they built it. We'll be uncovering the brilliant, iterative problem-solving process that literally took them from basic, bare-bones prototypes all the way to highly complex, competition-ready underwater vehicles.
Okay, let's dive into this. The Nemo ROV isn't just a random collection of thrusters and acrylic. What we're looking at here is the final product born from months of hard-won engineering victories. It's the result of rigorous prototyping, countless pool tests, and honestly, over 1,000 student hours of pure dedication. Looking at the reality of this hardware really grounds us in what this 14-member student team from Shanghai actually managed to pull off. To make sense of this incredibly complex robotic system, we're going to break it down into digestible, logical chunks. We'll start with the Oceaners robotics mission, move into architecture for Nemo and Tolkien, tackle iteration and trade-off analysis, explore control and distributed networks, highlight their core innovations, and finally, wrap up with the Oceaners safety philosophy.
Section 1. The Oceaners robotics mission.
Now, what's really interesting about this slide is how, to conquer the intense requirements of the 2026 MATE ROV Ranger competition, this team of 14 students had to cleverly split their focus. They had to manage two entirely different operational philosophies at the exact same time. On one hand, you've got Nemo, a highly maneuverable tethered ROV sporting an 8-thruster vectored layout that's designed for manual and collaborative control. But then on the other hand, you have Tolkien, a completely autonomous profiling float based on an ESP32 microcontroller, and it's engineered for totally independent vertical profiling and data transmission. So that's two completely different machines built in parallel, all for one unified mission.
Section 2. Architecture for Nemo and Tolkien.
You know, underwater, your physical layout absolutely dictates your maneuverability. It defines your limits. Because of this, Nemo utilizes an incredibly impressive 8-thruster vectored propulsion system. You have 4 horizontal thrusters and 4 vertical ones. And what this means in the real world is that the ROV literally has full 6 degrees of freedom. We're talking independent pitch and roll control here. When you're navigating incredibly confined underwater spaces or trying to maintain perfect stability in a shifting current just to scan a coral garden, that level of multidirectional control isn't just a luxury, it's an absolute necessity.
Section 3. Iteration and trade-off analysis.
So, the crucial point is that great engineering is fundamentally about the crucible of iteration. It's about building something, watching it fail, analyzing the trade-offs, and evolving the design to be better. Take their structural frame, for example. Generation 1 was built with traditional PVC pipe. It was cheap, it was fast to assemble, but it had measurable flex under load. And when a frame flexes underwater, your thruster alignment shifts, which completely ruins positional accuracy for delicate tasks like coral manipulation. By Generation 3, they transitioned to a CNC machined aluminum frame. Yeah, it cost more and took way longer to make, but it provided 40% higher stiffness. That 0.1 millimeter accuracy is exactly what makes repeatable, complex underwater maneuvering possible in the first place. And we see this exact same before and after iterative process happening in their software too. In their Generation 1 video pipeline, which used FF and PEG, they were experiencing around 300 milliseconds of latency. Now, a third of a second might not sound like much to you or me sitting here, but when you are piloting a fast-moving robot underwater, that lag causes terrible overcorrection. It leads to incredibly unstable control. By Generation 3, they completely optimized their pipeline using GStreamer, and they dropped that latency down to just 50 milliseconds. Solving that massive lag was an absolute game changer for the pilots driving the ROV.
Section 4. Control and distributed networks.
As the physical ROV got more and more capable, the software suddenly had to handle multiple heavy computing tasks simultaneously. Stuff like video streaming, motor control, and data analysis. The solution they came up with is just fantastic. Instead of cramming all that processing onto one single, completely overwhelmed laptop, they built a distributed topside control cluster using a 5-port gigabit network switch. They distributed the underwater video streams via multicast. This brilliantly prevents bottlenecks and allows multiple team members to work in parallel. Think about it. The pilot can focus strictly on navigation, while at the exact same time, on totally different computers, a modeling specialist is reconstructing a 3D coral garden, and a data analyst is estimating iceberg threat levels. It's a literal masterclass in dividing and conquering computational load. And this distributed philosophy extends right down into the ROV itself through a hierarchical control system. Step 1 is the topside control station up on the surface, handling the joystick inputs and the video display. Step 2 is the onboard Raspberry Pi down in the ROV, which acts as the middleware, relaying communications and handling the heavy lifting of the video streaming. And finally, Step 3 is the STM32 microcontroller, which is dedicated entirely to executing low-level, real-time, closed-loop PID control of the thrusters based on sensor data. By intentionally separating the topside interface from the low-level thruster execution, they guarantee that even if a surface computer lags or outright crashes, the ROV remains perfectly stable in the water. And this brilliantly illustrates the brains of the operation side by side. You've got the Raspberry Pi managing all the data-heavy tasks, while the STM32 microcontroller precisely fires the thrusters. It's just a perfectly balanced division of labor, safely housed right inside the ROV's waterproof enclosure. Section 5. Core Innovations. What truly sets top-tier engineering teams apart from the rest is when they make that leap from using standard off-the-shelf parts to fabricating bespoke, custom solutions. A prime example of this is the electronics they used for the Tulkin autonomous float. Rather than buying expensive, fully integrated commercial solutions, the Oceaneers team actually designed these ESP32 control and motor driver boards completely in-house. Not only did this drastically reduce their costs, but it perfectly tailored the electronics to the exact vertical profiling needs of their specific float, complete with clearly defined inputs to make debugging a breeze. Another absolute standout core innovation is Nemo's end effector. They developed a custom 3D printed modular gripper, but here is the real genius part. They utilized flexible materials in the finger sections. In a real-world application, a rigid metal claw might easily crush fragile mission objects, but these flexible fingers adaptively conform to irregular surfaces, safely distributing the contact force. It allows the ROV to securely pick up delicate simulated coral without causing any damage whatsoever. Section 6. The Oceaneers' Safety Philosophy. Now, all of this incredible innovation means absolutely nothing if the system isn't safe. The Oceaneers team baked safety right into their design from day one, protecting both the operators and the environment. Their safety features rely heavily on clever physics and smart electrical design. By placing the center of buoyancy, the foam, high up, and the center of gravity, the heavy battery components, down low, the vehicle is passively stable. It naturally just wants to stay upright. They also tuned it to have a slight positive buoyancy, meaning if the ROV loses total power, it won't just sink to the bottom, it will safely and slowly float back to the surface. Add in some distributed strain relief on the tether and hardware fuses on the power inputs, and you've got a deeply resilient machine. Let's move to and see how this builds directly into their operational safety. Notice those bright orange 3D printed PLA guards surrounding the thrusters? They serve a crucial dual purpose. First, they protect the ROV's internal mechanisms from foreign object entanglement while underwater, and just as importantly, they protect the human operators from accidental contact with spinning blades during deployment and recovery up on the pool deck. Which leaves us with this final thought. We've seen how the Oceaneers team totally moved away from centralized, rigid builds, instead fully embracing distributed gigabit networks, custom silicon, and highly iterative, flexible designs. When you look at the sheer ingenuity displayed by these student engineers, you really have to wonder, as these highly adaptable, human-in-the-loop systems scale up, how will they ultimately redefine the future of our deep-sea exploration? It's a fascinating question, and one I'm sure these very students will help answer in the years to come. Thanks for learning with me today, and I'll catch you in the next explainer.